Welcome to the AI Checkpoints. Before we jump into today's deep dive, just a quick heads up. This content, including these voices you're hearing right now, is generated by AI. We're here to synthesize and present information, not really to interpret or endorse it. So today we're tackling something pretty big in the AI world. For years, the absolute top-tier image generation models, the ones everyone benchmarks against, they've all been closed source.
Kept under lock and key, basically.
Exactly. But now, Tencent has dropped HunyuanImage 3.0. And they're not just saying it's good, they're claiming it's the largest and most powerful open source image model out there today. So our mission for you listening in is pretty straightforward. We're going to unpack the technical report that they released. We want to figure out why this model is getting that title and what specific technical tricks they use to get an open source model up to par with the big closed systems.
And that context is really key here. I mean, think about the heavy hitters, Seedream 4.0, Nano Banana, GPT-Image. They're amazing, no doubt. But they're black boxes. You can't really see inside, which limits research, makes auditing hard, So HunyuanImage 3.0 being open source and hitting that performance level, that's actually a significant move for the whole research community. It opens things up.
Let's get into the nuts and bolts then, starting with the architecture, because the scale is just huge, but they claim it's efficient too. It's built on a Mixture-of-Experts LLM backbone called Hunyuan A13B.
That's right. And MOE Mixture-of-Experts, it's all about scaling up capacity without blowing up the computational cost proportionally. The total parameter count is massive, over 80 billion.
80 billion. Okay, that immediately makes me think, how on earth do you run that efficiently? Sounds computationally brutal.
Well, that's a clever part of MOE, isn't it? During inference, like when you're actually asking it to make an image, it only activates a fraction of those experts. Specifically, just 13 billion parameters light up per token. So you get the, let's say, modeling power of that enormous 80 billion count. But the speed and the cost feel much more like a 13 billion parameter model. It's a trade-off, balancing capability and usability.
Right, balancing act. So they've got the scale sorted. But you mentioned innovation. The big one seems to be how they combined text understanding and image generation into one system, natively multimodal, we call it.
Exactly. It's designed from the ground up to handle both understanding different modalities and generating them, all within a single autoregressive framework. Think of it like a hybrid system.
Okay.
For TAC tokens, it works like a standard language model reads sequentially, predicting the next word. But when it hits image tokens, it switches its approach.
Yeah.
It uses a diffusion-based prediction method, which is much better suited for creating complex visual details.
Merging those two approaches, sequential text and sort of global image generation, that feels like it would create problems, especially for attention mechanisms, right?
Yeah.
How does the model know what to focus on?
That's a core challenge they tackled with something called generalized causal attention. It's pretty neat.
Okay, break that down. Generalized causal attention.
So standard LLMs use causal attention. A word can only look back at the words that came before it. Simple, sequential.
Like reading a book.
Exactly. But for images, you need to see the whole picture at once, right? Understand how things relate globally, composition, lighting across the scene. That needs more like full attention.
So how does this generalized version handle both?
It's adaptive. For text tokens, it sticks to the normal causal rules, preserving that sequential understanding. But when the model processes an image segment, the image tokens get special permission. They can attend to all the other image tokens within that same segment.
Ah, I see. So it keeps the text logic, but lets the image part see everything they need to.
Precisely. It respects the text flow while giving the image generation part the global context it needs to make a coherent picture.
And coherence also means knowing where things are spatially. Which brings us to another piece of the puzzle. The generalized 2D ROPE scheme, position embedding.
Yeah, ROPE, rotary position embedding, is standard for 1D sequences like text. Tells the model the position of each word. But images, they're 2D. Obviously.
Need coordinates, not just a sequence number.
Exactly. So what they did was they took the standard 1D ROPE signals and effectively reshaped them into 2D coordinates specifically for the image tokens. The technical report shows this in Figure 5.
Clever. Did that break the text part?
No, and that's the elegant bit. It's backward compatible. When the model is only dealing with text, it just defaults back to the original 1D ROPE.
Yeah.
So they added spatial awareness for images without messing up the pre-trained language abilities of that big LLM core. Smart engineering.
Okay, so we've got this massive, efficient hybrid brain with clever attention and positioning. The best architecture in the world falls flat if the data it learns from is, well, garbage.
Could agree more.
Let's shift to the data side then. Section 2 of the report goes deep on data curation, and it sounds like they were incredibly strict.
Meticulous is the word they use, and it seems justified. They started with a pool of over 10 billion raw images.
10 billion.
Yeah. And after their whole filtering process, they kept less than 45%. That tells you how much they threw away to ensure quality. Section 2.1 really lays out this three-stage filter.
What were the main things they were trying to get rid of? I saw they specifically targeted AI-generated content, AIGC. That seems important now.
Hugely important. So stage 1 was basics, low resolution, bad exposure, duplicates, technical stuff. Stage 2, the main curation, was about content. They use models to detect watermarks, logos, too much text using their own OCR model, and crucially, yes, specialized detectors to weed out AIGC.
Why is filtering out other AI's images so vital? Doesn't more data usually help?
Not if it's the wrong kind of data. If you train on too many synthetic images, the model can start learning the flaws or stylistic quirks of other AI models. It's like learning a copy of a copy. You drift away from the real world's visual rules. Removing AIGC helps keep the model grounded in actual reality.
Okay, that makes sense. And they didn't just use automated filters. They actually brought in artists to help design an aesthetic scoring model. That sounds unusual.
It is a step further than many take. Instead of just using a generic, does this look good model, they had artists define criteria based on fundamental principles. Color theory, light and shadow techniques, composition rules, things artists actually use.
So the aesthetic score wasn't just some black box number. It was based on real artistic judgment.
Exactly. Grounded in established visual principles. The goal was to ensure the training data wasn't just technically clean, but also met a high bar for visual quality, leading to better output later.
Right. Quality images are one thing, but controlling the output needs good descriptions, good captions. They aimed for rich, controllable, and factually grounded captions. How they achieve that?
They developed a pretty sophisticated captioning system. It's bilingual, first off, and uses a hierarchical schema. So instead of just one sentence...
Like a cat sitting on a mat.
Right. They broke it down into multiple fields. Detailed descriptions, yes, but also specific stylistic tags and, importantly, factual entities. These are proper nouns, think specific landmarks, brand names, recognized objects.
Making sure those facts are actually correct sounds like a challenge. That's where the agents came in. Figure 2 shows this factual grounding pipeline.
Correct. They use helper agents. An OCR agent reads any text within the image itself, and a named entity agent, or IP agent, cross-references things like landmarks or brands against external knowledge bases, checking the facts.
Okay, so the agents provide external knowledge.
But here's the really clever part, what they call the bidirectional verification loop. This, I think, is a key differentiator.
Bidirectional verification. Tell me more.
It's like a double check for consistency. The system generates a detailed caption based on the image. The agents provide external facts about the image. Then, the system cross-references the generated caption against the agent's external knowledge.
Ah, so it checks if its own description matches the external facts.
Exactly. If there's a mismatch, if the caption says it's the Eiffel Tower but the knowledge base disagrees, or if the facts don't align with the visual evidence, the whole image caption pair gets tossed out. Only samples where the internal description and external facts perfectly align are kept.
Wow. That builds in a serious layer of trustworthiness. Ensures the model learns accurate connections between words and real-world things.
Precisely. It's vital for getting the model to follow instructions accurately, especially when prompts involve specific known entities.
So that handles factual grounding. But complex prompts often need more than just facts. They need reasoning, right? Like understanding relationships or abstract concepts. They train the model for chain of thought, CT. How does that work in practice?
COT is basically teaching the model to think before it generates, to plan. So if you give it a complex prompt, say, a retro-futuristic diner scene at dusk with a chrome robot waitress serving a glowing blue milkshake.
Yay.
Instead of just jumping straight to pixels, the COT-enabled model performs an intermediate step. It sort of refines the concept internally. It breaks down the prompt into key elements and their relationships. The retro style, the dusk lighting, the robot's material, the milkshake's color and glow. It forms a plan.
And this planning ability came from specific training data.
Yes, they fine-tuned it on specialized data sets, both text-to-text data, but crucially text-to-text to image data. This T2TI data included examples of prompts paired with explicit reasoning steps and the final image. It learned how to bridge that gap from abstract request to concrete visual plan.
So it learns how to interpret and break down complex instructions.
Exactly, which significantly boosts its ability to follow nuanced multi-part prompts and handle logical relationships within the image.
Which leads us neatly into evaluation. If they're claiming parity with the big closed models, they need solid proof. But the report actually critiques standard benchmarks like T2iCompBench and GenEvolve first. Why aren't those good enough?
Well, their argument is that those benchmarks often use very short, simple prompts, and they rely heavily on automatic scores like CLP score.
Which measures how similar the image is to the text prompt semantically.
Right. But CLAP score, as the paper points out, is pretty bad at judging spatial relationships or complex compositions. It might see cat and fence and give a high score, even if the prompt said cat behind the fence and the image shows it in front. It misses the structural details.
Okay, so the old metrics aren't sensitive enough for complex instructions. Their answer is this new metric, SSA Structured Semantic Alignment Evaluation. Sounds fancy. Is it just another custom benchmark?
Well, it's custom, yes, but the methodology seems quite robust. They didn't just invent a score. They took 500 diverse, complex prompts and used powerful LLMs and multimodal LLMs to break each prompt down into around 3,500 specific key points.
Wow, 3,500 points from 500 prompts.
Yeah, and categorized across 12 detailed fields.
Hmm.
Things like, what are the main nouns? What are the scene nouns? What's the requested composition? Specific details.
So instead of one vague score, it's checking off dozens of specific requirements for each image.
Exactly. An MLLM then uses chain of thought, there it is again, to meticulously score the generated image against each of those fine-grained points from the original prompt. It's a much tougher, more objective test of actual instruction following.
And how did HunyuanImage 3.0 do on this SSAE test?
The results shown in those radar charts in Figure 6 are pretty compelling. It performed neck and neck with top models like Seadream 4.0 and GPT-Image across almost all those detailed categories for both English and Chinese prompts.
Okay, that's strong evidence, but ultimately people decide if an image is good.
Right.
They did human evaluations too.
It did. They used the GSB method, good, same, bad. Had over 100 professional evaluators compare images generated from 1,000 different prompts.
Comparing HunyuanImage 3.0 against the closed models.
Yes. And the results, which you can see in Figure 7, really backed up their claim of parity. HunyuanImage 3.0 actually had slight positive win rates against the commercial big guns, 1.17% over Seadream 4.0, 2.64% over Nano Banana, and 5.00% over GPT-Image.
So human judges rated it as good as or slightly better than the leading closed systems. That's quite an achievement for an open source model.
It really is. It suggests the combination of architecture, data, and training has genuinely closed the gap.
Let's quickly touch on that training process. Table 1 shows they used progressive training across 4 stages. What was the idea there?
It was about gradually increasing complexity. They started training the VAE, that's the part that compresses and decompresses the image at a lower resolution, 256 pixels. Then they progressively increased it up to 124 pixels on the shorter side by stage 4.
Start simple, then add detail.
Sort of. It lets the model learn the basics efficiently in that compressed latent space before tackling higher resolutions. They also layered in the more complex tasks like the chain of thought fine-tuning only in the later stages once the foundations were solid.
Makes sense. And after the main training, they used a bunch of post-training refinement techniques. Lots of acronyms here. DPO, Mixture-of-Experts, SRPO, REDA. What was the goal of all that?
Polishing. Really aligning the model's output with human preferences for things like aesthetics, realism, and making sure it strictly follows the prompt. DPO, direct preference optimization, is interesting. It learns directly from human preference pairs, like this image is better than that one, without needing complex reward modeling sometimes.
And the others. Mixture-of-Experts.
That's an online reinforcement learning method. It uses specific reward models, separate models trained to judge things like beauty or accuracy, to continuously provide feedback and tweak the main model's outputs. SRPO and REDA seem to be their own in-house methods, likely designed to push realism and visual clarity even further, tackling those last few percentage points of quality.
So a multi-pronged attack to iron out any remaining visual flaws or alignment issues.
Exactly. Fine-tuning based on direct preference, reward signals, and custom techniques.
And one last technical insight. They looked inside that MOE brain again, analyzing which experts were firing for different tasks. Figure 8 shows this.
Yeah, expert activation discovery. It's quite fascinating. They found that in the earlier layers of the network, the experts were more generalist. But as you go deeper, they become highly specialized.
Specialized how?
Some experts ended up primarily processing image tokens, while others focus almost exclusively on text tokens. The deeper the layer, the more pronounced this separation became. They measured it using KL divergence.
So the MOE structure naturally encourages specialization for different modalities.
That's what the analysis suggests. It implies the MOE design isn't just for efficiency, it really helps the model become better at handling multimodal inputs by letting different parts focus on different types of information. A nice bonus.
Okay, let's wrap this up. What's the big picture here for you, the listener, the researcher, the developer?
I think the main takeaway is pretty clear. HunyuanImage 3.0 represents a major step forward. It's huge, it's powerful, it uses incredibly stringent data cleaning, advanced reasoning like COT, and some smart architectural tricks like generalized causal attention.
And critically, it's open source.
Right. Achieving performance that rivals the best closed systems, but doing it in the open. That's huge for transparency, for reproducibility, for letting the whole community build on this work. It really levels the playing field.
Absolutely. And maybe a final thought to leave you with. The report explicitly mentions that while this text-to-image capability is out now, they're still training the image-to-image and broader multimodal functionalities and plan to release those soon.
So understanding and editing images too. Exactly. Now, think about that unified architecture we discussed, designed from the start to handle text and images, generation and understanding, all interleaved together. What could the user experience actually look like when that full capability is unlocked and released? Imagine having a conversation with the AI, asking it to generate an image, then discussing that image, asking for specific edits, maybe even feeding it another image to incorporate, all seamlessly within one continuous flow.
That sounds like a genuinely interactive creative partner, not just a generator. A very powerful possibility indeed. Definitely something to think about. Okay, that's our deep dive for today. Hit like and subscribe if you like the content. See you next time.